Right, we're going to look now at the product rule and quotient rule of differentiation. As they suggest, rules that help us differentiate products of functions and quotients or fractions of functions. It's going to be really useful for us. So we'll get stuck straight into it, and I'll show you what the product rule is. So the derivative. So this is the product rule. This one here. The derivative of a product of two functions. I'm going to call them u and v. Now I'm just following here what the material in the syllabus and the textbook follow. U and v, not great letters to use because they look a lot alike. But the derivative of excuse me, function that where u and v are both functions of x. Okay, so maybe I'll just make that point as well. Right, u is equal to a function of x, and v is equal to another function of x. Okay, but it's easier just to write them as u and v. Really straightforward one. Equals u v dash, so hold u, derive v, and then sum the opposite, u dash v. U v dash plus, I'm always going to say it as vu dash, so I'll write it like that. Vu dash. That's it. That's the product rule. The quotient rule is slightly more involved. Right, and this says that the derivative of u over v, same deal, u and v functions of x, equals, start with a v, vu dash minus this time, u v dash over v squared. All right, let's have a look at how these work, because at the moment that's just a load of gibberish. All right, so look at an example that we actually don't need to use the product rule for. So example, derive, let's say x squared x plus 1, right, y equals that. Okay, we don't need the product rule for that. We're going to use it, but we'll also derive it the way we know how, because if we were given this question, we'd just expand it out. In fact, let's do that. X cubed plus x squared, and then we go y dash equals 3x squared plus 2x. So it took us seconds. So there'd be absolutely no reason to use the product rule here. The only reason I'm going to get you to do so, or I'm going to show you how it's done, is because as we've talked about before, if we can come up with a known result, and we can use some other method, then it sort of validates that method. So in this case, we're going to use the product rule. U is equal to x squared, so that's my u. My v is x plus 1. You see I've got the product of two expressions, x squared and x plus 1. I can use a product rule for this. So y dash is equal to, here we go, u v dash plus vu dash, right? So u stays as it is, so that's x squared. V dash, now I'm going to derive x plus 1. Well, that's just 1, isn't it? Alright, so I'll put brackets around just to know that x squared times 1. Now I'm going to go the other way. V is going to hold, x plus 1. U dash is 2x. Expand this out, you've got x squared plus 2x squared plus 2x. And if you combine like terms, you've got 3x squared plus 2x. And you can see we get the same result. Okay, so that's a product rule and how that works. I could show you that, but I'm sure you believe me. Right, let's do some examples. The most useful when you so find the derivative of, right, let's go with textbook examples. 3x plus 1 ln x. Right, this is good because we don't have the option here of no, we could expand this out, but we don't have a method by which we can derive this without using the product rule. So we're going to let u equal to 3x plus 1. All right, that's my u, and that's my v. So my fx, my f dash x will equal u, 3x plus 1, v dash. Right, v dash, remember what the derivative of log x is? It's 1 on x. Plus v ln x, u dash, that's 3. So let's just tidy this up. 3x by 1 on x, that's 3x on x, that's just 3 plus 1 by 1 on x is 1 on x, plus 3 ln x. So 3 plus 1 on x plus 3 log x is my derivative there. So that's f dash x. Now let's have a look at another one. It's x. So for our second example, we're going to look at using the quotient rule now. So in this case, in the quotient rule, we allow the numerator to be u and the denominator to be v. No choices there. That's got to be in that order. And also, look, we've got a fraction here. I don't know how else you'd do this. We certainly can't, as some people like to do, differentiate top and bottom individually and represent that as the derivative. That's not a happening thing. We can't do that. All right, this is y equals. So let's now use our quotient rule to find the derivative here. So y dash equals. Right, let's have a look. So how does it work? It went v x squared plus 1. Right, so this is it here. We're using v u dash minus u v dash. So v is x squared plus 1. U dash is 5. All right, so v by u dash. Now I'm going to subtract u, 5x plus 3, by v dash, which is 2x. All right, that's all in my numerator. Denominator is v squared. X squared plus 1 all squared. Don't need to worry about expanding that out. All right, let's just look at the numerator and tidy that up. 5x squared plus 5 minus 10x squared plus 6x, because that 2x is by 5x, which is minus 10x squared. Actually, that's a minus 6x there, isn't it? It's a minus 6x. Thanks for pointing that out. So because it's this 2x could be sitting out the front, minus 2x by 5x minus 10x squared minus 2x by 3 minus 6x all over x squared plus 1 all squared. More tidying to do. 5x squared minus 10x squared is minus 5x squared. Then we've got minus 6x plus 5 all over x squared plus 1 all squared. Okay, so there's our product and quotient rule. Just to recap, our product rule, u by v, product of two functions of x. And all we need to do is hold one, derive the other, and use the product of those two, and sum the reverse. The vice versa, the v holds and u gets derived. So just take those two functions and run that through for a quotient of two functions. We start with our denominator and we leave that alone and multiply by the derivative of the numerator, subtract the reverse, put it all over the square of the denominator. Get some practice at that and you'll be fine. A couple of examples there. These are the questions I'd like us to do from the next two exercises. Plenty of practice at deriving such functions, and we'll need a day or two to get through that. So I'll see you in class.